Hello and welcome to another part of the Joe Trohman modding vlog. Your host Damon Standing, and this time we're doing the wiring. I'm not talking like actual wiring, I'm talking about the theory of the wiring. So bear with me, and I hope I present this at a level that's suitable for whoever's watching. I'm only going to cover stuff that is used in this guitar, but it's pretty much everything gets covered. So without further ado, let's get started with this wiring vlog. Okay, so in front of me I have prepared a big bunch of wiring diagrams and sound theory diagrams. This took quite a few hours, and that's making me not sure how long this is going to be, but let's get started, I suppose. So here is the wiring diagram of the Joe Trohman signature model now. I didn't take a copy of it while it was put together. And just as a note, this is how you'd see it through the pickguard, looking through the front, except for the pots, which I've done what you see from the back of them, but because otherwise it's really confusing, because you can't really solder to the top of the pot sort of thing, because there's pickguard in the way. But yeah, here we have the kill switch, the north coil humbucker, south coil switches for both. Each of the pickups as an inductor, labelled with their polarity. Then the phase 1, phase 2 and bypass parts of the switches. The series parallel connections between this pair and this pair. The baritone, the treble bleed mod through the 5-way switch, which has 4 poles but I only used 2. Here's the inductor used for the baritone. Then we've got the volume pot, the tone pot, the wire that goes under the bridge to ground the strings, and the wire that goes to the cavity shield. So I'm not sure about you, but this looking at this is quite overwhelming, so I do have a breakdown of every single part over here. But first I'll go through a couple of universal things. Firstly, the only quirk in this guitar is that if these are connected to bypass, then they're sent to ground. However, if that's in parallel, then that ground is connected to this line, and this line is basically the line of the signal that goes to the pot. Now, if this is ever connected to ground at any point, you won't get any output from the guitar, and that's the principle of the volume pot. It connects it to ground, but I'll talk about that later. But that's basically the only quirk about that. So if you go in parallel with a pot, with a pickup that is bypassed, then you will short the guitar's whole signal to ground, so you just have to be careful. But yeah, that is the basic diagram of the whole thing, and if you want to follow that, you can. But what I'll do now is I'll explain how each of the different parts works. So let's go over to this piece of paper. Okay, let's start with the series parallel switches. So here is one isolated, and these are where they're located on the actual guitar. But basically, the way these kind of switches work, these are the slider switches. So just get a pencil to point, when the switch is on this way, then these two sets of poles are connected. When it's down, these two sets of poles are connected. So let's have the switch up, which will be in series. So you can see that there's the ground cold end of a pickup. There's a pickup, goes through the hot, and then this part is connected because the switch is up, and that goes into the cold of the other pickup. So what you can see is that it's basically putting these two coils in series with each other. Series being in line with each other. So that's the signal path when this is in the series, and then this part gets connected, but it's connected to nothing, so this goes nowhere. It's effectively a zero join, and you just go through series. So here's one pickup, here's another pickup, and that doesn't really matter so much when you're in series, they're just coils. But now let's switch it down, connect to this line and this line in parallel. So what we find is that for this pickup, it goes down and through, out the hot, and then instead of connecting down here, it goes through from the ground to this point, and then this parallel can go to the master volume or the pickup volume. For this one, we see that this is the cold end, so this should be connected to ground. So now, as this one is connected to the master volume or its own pickup volume, this one is the cold end of this pickup is connected to ground, and then in turn the hot end can be connected to wherever it wants to go, so maybe the master volume or the pickup volume. So what we see here is basically here's one of the switches, it goes in parallel, this is connected to ground, and what happens basically is this comes through the pickup and is connected to this line, which is the parallel line to the volume pot. So I'll just go over that once again. In series, these two are connected, that's the switch up. This one is one pickup, the hot goes into the cold of the next pickup along, and you form a two pickup series chain. When the switches are down, these are in parallel. So this pickup goes from hot and goes to a volume pot or other. And then the cold of this pickup is connected to ground, and then the hot end of the pickup will later meet up with the cold end of this pickup, and that will perform a parallel connection. Parallel is when the line splits, series is when things are added in the same line. So that's basically the explanation of the series parallel switches. Move on to the switches that are concerned with the coils on the humbuckers and the north coil, humbucker, south coil switch. So these are located here on the actual diagram, but here is a close-up of how one works. So this is this is a three-way slider switch. So when it's in this position, these two poles are connected. When it's in the middle position, these two poles are connected, or these pairs of poles are connected to each other. And when it's in this one, these pairs of poles are connected. So what are we doing here? Here's a master hot. Let's say that is what goes to the pot. Is the master cold. Let's say that's what would go to ground. So let's have it in the middle position, which will describe a humbucker. So we come in through the cold. We go along here. This is connected to the cold, but it doesn't go anywhere. So we go along here. We go into the cold of the north coil. We come out the hot. Then this wire connects these two poles of the switch. And that goes into the cold of the south, comes out the hot, then is connected to the master hot. So what we have here now is a series connection between these two in phase. So cold should always be one way, hots should be the other way. Colds connect to hots, basically. So here's the master cold. I'll trace that out again. So this would go to ground, and this master hot would go to the volume pot. So we go connected here. We go through the cold, through the pickup, out of its hot, and connects to the cold of the other coil of the pickup, out of its hot, and go into the master hot, which will go to the volume. So that forms a humbucker, because it connects both of the coils in series. So let's put it on one of the coils. So let's have the switch going this way and connected to... Oh. Sorry, I accidentally cut the recording there. So let's have these two, the switch pushed this way. So it's connected here and here. So this should connect only the south coil. So let's come in through the cold. If we go through the cold, it goes this way, but it doesn't go anywhere. So it goes into the cold of the south coil, out of the hot, and then here. But this is connected to here, because the switch is this way, and it comes round out of the master hot through this little shorting wire. So let's do that again. Master cold goes along from where the switch is in place, goes to the cold, through the south coil, out of the hot, gets back to the switch, then it comes round through the shorting wire to the master hot. So as you can see, that selects south coil. So let's do it on the other side. So here's the north coil. These two are now These two pairs are now connected. So you come in through the cold, and before you can get to the switching point, you jump in this wire, and that brings us back to here because these are connected. These pairs are connected. So you come in through the cold, goes through the shorting wire, comes back through the switch, then into the cold of the north single coil, or north side of the humbucker, out of the hot, and then is connected straight this way through the master hot. No, out through the master hot. And you think it might go this way, but none of these are connected. So let's do that again. Master cold comes out, goes through the shorting wire, comes through the switch, goes into the cold, goes down through the north coil, out of the hot, and then goes to the master hot. So that's basically how that works. I'll just trace those all out again. In the middle position, we have humbucker. So you come out the cold, follows this line, goes into the cold of the north coil, out the hot, into through this shorting wire, cold, south, hot, the master hot, and that's basically how it all works. So now let's move on to the third kind of switch being used, which is the bypass phase 1, phase 2 switch. Okay, so these are the bypass phase 1, phase 2 switches, which are effectively the on-off switches for the pickups, and they are located here on the main diagram. So what do we have here? We basically have another three-way switch, so they're connected. When it's this way, these pairs are connected. When it's in the middle, these are connected. These pairs are connected. When it's this way, these pairs are connected. So let's start with the most obvious one, which is the bypass. So that's fully this way. This goes to the cold of the next pickup, or if you're in parallel, it would go to, well, no, it goes to the cold of the next pickup, because otherwise you'd short it to you short the system to ground if you're in parallel. So this goes to the cold of the next pickup, which would be selected via the series parallel switches. So these go around to one of these series parallel switches, and the other one is connected to the other side of this. So basically, here we start with the ground, or the master cold, or from the hot of the last pickup. And so here it just goes through a wire and out. This pickup isn't used. So that is in the bypass position, fully this way. So let's go into the middle position, which is where these pairs are connected. You come out of the cold, or you come from the hot of another pickup, or ground, and then it goes into the cold of this pickup. We'll ignore the polarity of the coil, of the pole pieces, out of the hot, and then into the cold of the next pickup. Now, this is the clever part. When you put it into the right position, this isn't connected anymore, but it does have a short wire. So we come in through, and then we go into the hot and out of the cold. So what you see here is if we have it in the middle position, we come in through the cold, out of the hot and out. If we have it in the right position for the second phase, you could argue reverse phase, but phase is all relative. You go into the hot and out of the cold. So basically this turns the pickup the other way around, and we'll discuss phase theory a little bit later. So the way these integrate with the series parallel is, you see here, here goes with the pickup, which is integrated with the master cold, master hot, north coil, humbucker, south coil switch we were talking about. So it comes in there, there's where your pickup is connected. And so here's a ground, or the cold of the next pickup. And then this leads to pickup 1 in this diagram, if you see. So when you put it into series, this wire leads to the bypass phase 1, phase 2 for pickup 2. And now you can see why, if you put it in parallel and have this one, well, if you have one of them switched off, this gets connected to ground, because this connects in parallel, round, then off, goes to ground. So your signal is at ground, that means you have no output. But if you have them both on in parallel, they end at ground here for this pickup, and ends at ground here for this pickup. And so it doesn't connect to ground on the same side as here, so they get a parallel connection and you do get a sound. So before we go into phase theory and all that kind of stuff, that's basically how the pickups are all connected. So let's go into some of the more basic extra components like the volume, tone, kill switch, and then we'll discuss some of the treble bleed and baritone choke mods. Okay, so here is the volume, tone, jack and kill switch set up. This can be found after the pickups, which just go straight into the volume pot on a parallel line or series line, depending on how it ends up being connected. So what do we have here? Here's from the pickups into the middle of this volume pot, which in this case was a 250 kilo ohm audio taper. What you'll find is pots are usually labelled their value, then A or B. A stands for audio taper, which means that the resistance isn't constant the way you go around here, as in the rate that the resistance changes isn't constant. Then you have, if it's labelled B, it's linear, so the rate that the resistance changes is like, it stays the same as you turn around. But that's a consequence of parts, and we won't really discuss that too much. So what you see here is that when the pickup is when the volume control is at 10, these are connected without any resistance. And there's a high resistance to ground, between this and ground. So the signal takes the path of least resistance, and that's basically your volume all the way up. Now when we turn the volume all the way down, these are connected, and this is connected straight to ground. So what we find is we have no output because there isn't any potential difference. Potential difference being the voltage between what you consider to be your live and your ground. And everything is oscillating between live and ground because it's audio signal. So let me just repeat that again. When your volume's at 10, these are connected with zero resistance, and you have a 250 kilo ohm resistance to ground. So it takes the path of least resistance and you get a signal. Now if you turn your volume all the way down, these are now connected with no resistance, so you have no resistance to ground, thus you have no signal because you're connected to ground, you've got zero voltage. So let's move on to the tone knob. So this is the output of the volume, and this ends up coming to ground. This ends up, sorry, not coming to ground. This ends up going to the live pin of the jack. Now, what we also have connected to that is the tone part. And what that basically does is when the tone is up part is all the way at 10, it's connected to this blank terminal, so nothing's happening. Except there's a 250 kilo ohm resistance between your main signal and a capacitor which is going to ground. So the capacitor, which is usually 0.047 or 0.022 microfarads, that basically bleeds a load of the treble part of the signal out into ground. So if you turn your tone all the way down, this resistance is near to 0, and basically it sucks out the treble tone from your line, and you're left with a very bassy signal, well, very treble lacking signal at your output. So let's go over that again. Basically, when your tone is at 10, it's got a 250 kilo ohm resistance for this type of part between a capacitor leading to ground. So obviously it's always going to take the path of relief resistance, which is straight to the jack. So there isn't that much effect to your tone. But as you turn it down, this resistance gets smaller towards the capacitor, and when it's all the way down, the capacitor just bleeds out a portion of the signal to ground, which, since it's a low pass, but I'll discuss that in a minute, basically dulls your tone down because it's taking out all the treble, a lot of the treble frequencies. So in addition to that, your volume and your tone part are connected to ground, and then ground is connected to ground at the back of the tone parts. Now what we have here is the kill switch. So this basically is a small switch that just connects these pins or these pins together. So when these are connected together, nothing is connected. Well, it's funny to say, but basically ground is connected on the switch, connected to effectively nothing. So it's just a floating ground. But when you engage it this way, what you do is you connect your main signal to ground, and just like what we discussed when you accidentally put a pickup in bypass in parallel, you connect it to ground, it connects the signal to ground, and thus you have no signal. Thus it kills your signal. Kill switch. So that is basically how a volume, tone, jack, and kill is wired, and you can have volumes and tones for separate pickups. I guess you can also have kill switch for different pickups, but that kind of defies the point of a master kill switch. You may as well have pickup on and offs like over there. So now we'll discuss the treble bleed mod and the varitone. Okay, we're back. So let's discuss the extra little features, being the treble bleed volume and the varitone choke. So here is the treble bleed volume. It's basically a volume with the input and output shorted with a 100 kilo ohm resistor and a 0.002 microfarad capacitor. So what this basically does is, well, the 100 kilo ohm corrects for the taper, because if you short two terminals, you can change the rate at which your volume is turned down, because there's a difference in resistance. So that's, ignore the 100 kilo ohm, but that basically corrects the reactance, let's say, the way the pot reacts, because reactance isn't an actual term in electronics. But the 100 kilo ohm resistor basically corrects the way the pot acts while there's this capacitor in place. But what this capacitor does is it's a very low value, and that basically allows frequencies that are pretty high to bleed across this terminal. So when your volume pot is all the way up, these are connected, and it's still going to take the path of least resistance. So you're just going to go through, there's going to be hardly any notice of this mod in place. But when you turn down, some of the signal's going to want to go to ground, some of the signal's going to want to go to the output, but as well, some of the signal is going to want to go through the capacitor, and that signal is going to be high frequencies, because your signal is like a range of frequencies. So what this does is means when you turn down your volume, it doesn't lose brightness, or it loses less brightness, and it can kind of account for or compensate for the loss of tone that you usually get from turning down the volume. So that's basically how the treble bleed volume works. It's just a capacitor of a very low value, so it's high frequency. We'll discuss how that works later. It's just shorted between the input and the output, and it provides a high pass for frequencies. So frequencies over that value you can pass through, and it basically just allows you to have a brighter volume at brighter tone at lower volumes. So let's move on to the baritone now, because essentially these get integrated together in my setup. So here's the parallel line from the pickups to the volume, and what we do is in parallel we short it to ground through an inductor in the form of a small audio transformer, and then a bunch of capacitors, or which we can select. And as you can see, I have another pole here, and that is the bypass position, so nothing is being choked out, because otherwise you'd always have a choke in place. So what's this really doing? I'll discuss that more in the baritone choke theory, but basically it allows a portion of the signal to be bled out through in parallel to ground through the main live line, and the values of the inductor and the capacitors combined dictate the frequency and the kind of span of the frequency, but I'll explain that later, of what gets bled out. So in my setup, I used 0.001 microfarad for what I referred to as position 8, and then a 0.047 microfarad in what I referred to as position 9. Sorry, not 9, 7, because it's on a knob. And then 0.01 microfarad on the position which I refer to as 6. But basically, these each perform a function of characterizing a frequency which will be bled out of the signal. So this is a low value capacitance, so this is a high frequency that's going to be bled out. This one's pretty high comparatively, so it'll be a lower frequency than that. And this one is in between the two, so this will be a middle frequency. This is the inductor, which is basically just a little audio transformer. And usually audio transformer is characterized by its value in terms of how it would be in terms of frequency. And what I was told by a colleague at work is that if it says 20,000 ohms, because that's a reactance, which is frequency times inductance in some form of relationship to imaginary and real parts of currents, but that's serious theory, so we won't think about that. But basically, if it says 20,000 ohms, what it means is what it will be is 2 henries, is what he told me, because the frequency that everything is measured by is most likely to be 10 kilohertz, because that's middle of audio frequency. Now, I'm not sure if that's angular or regular frequency, but let's say this is around 2 henries for the sake, or if not, it's 1 henry. So that's basically the wiring of baritone choke, and I'll show you this wiring in a second, which is how it's implemented in the setup on this guitar. Okay, so this is how the baritone is wired up in the actual setup. So these are two poles of a rotary switch, which was originally used for the pickups in the original wiring for the guitar. But here's the common, which there are technically two commons, but they're soldered together because it's just how this is going to work. But here's position 1, position 2, position 3, 4, 5. So these rotate around at the same time. So in position 1, we're in bypass. Here's the pickup line. Here's the parallel connection to the switch. Here's our volume pot, and then that goes to the tone pot, etc. So in position 1, there's no difference. We just go straight to the volume. This isn't connected to anything. So this is open circuit. Go through the volume and out. And this can also be done after the volume, but I chose to do it before the volume because I was told that the volume can react. Playing with the volume will react differently depending on where the baritone choke system is. So let's go to position 2. There's nothing connected on this side, but there is connected on this side the treble bleed mod. So here's our 0.002 microfarad capacitor, here's our 10 kilo ohm resistor, and this is effectively, if you just shorten this section of wire, it's just connected across like this. So this basically creates this mod, which is the treble bleed mod, and position 2 becomes the treble bleed. Now let's go to position 3, which goes to the first of nothing on this side, and then on the second pole, the first of the baritones. So you'll see I have here some resistors connected across each capacitor, and these capacitors are just in this order: 0.001, 0.001, 0.047, and 0.01 microfarad. And then there's just our inductor here. But yes, I have a 10 mega ohm resistor connected across each capacitor. Now this shouldn't really affect the tone that much, but basically what it means is when this, a capacitor stores charge. So what it means is that when I turn off or disconnect the baritone, this charge can bleed out of the capacitor and go to ground. And what this prevents is a popping noise when you flick the switch. And that popping noise is effectively a small spark. So this prevents that, and this was just recommended to me by a guy at work. The same guy who talked about this stuff, Anton Grounds. He's pretty damn awesome at RF and audio frequency and microwave frequency stuff. So yes, in position 3 we go to our first baritone. Position 4 we go to our second, and in position 5 we have our third. So that's basically how it's wired here. And if you remember from a little bit ago, this is a treble cut because it's a low frequency capacitor. This is a bass cut because it's a higher frequency capacitor. And then this is a middle-ish cut because it's somewhere between the two. So that's basically how the baritone is wired. So now let's go on to... Actually, no, we'll just make a little summary. So now I've talked about how the whole of this works. The baritone fits in here with a parallel connection of what becomes the volume from the pickup line. And so now let's discuss the actual theory of how all this stuff works. So, yeah. Okay, so first things first, let's cover humbucker theory. So we have, for all extensive purposes, we have these pole pieces, which are north-facing magnets, these pole pieces, which are south-facing magnets, and the coil is wound this way around the north and this way around the south. In actuality, these aren't north-facing magnets most of the time, and these what you find is that there's one big magnet, and then these are metal pieces, and it channels the north field and the south field out of the magnets. But for the purpose of this, let's assume that they are just south-facing and north-facing magnets. So in the north coil, you get this signal, Now this big signal, this big, is 50 hertz mains noise, or 60 hertz if you're in America. So that's the buzz, that's the hum, that's the that you get whenever you're playing with single coils, and sometimes with humbuckers, but to a lesser extent. And then this is the guitar signal. So this is produced from the strings interacting with the magnetic field of these pole pieces, which is then picked up by the coil. So what we see is, for the south coil, this noise is the opposite way around. And that's because the noise is picked up by the coil. If the coil's one way, the noise will pick it up that way. If the coil's the other way, it will be picked up in the opposite way around. Now the clever part is that these are north-facing magnets on one side, and these are south-facing magnets on the other side. So when the string disturbs the magnetic field and is picked up by the coil going this way, it's the opposite on this side, on the south side, an opposite displacement of the magnetic field. But the coil is also going the other way, so since the pole is switched and the coil is reversed, it makes the same signal as for the normal. It's like two negatives make a positive. But since the magnets don't actually affect the pickup of the noise, they are the opposite way around because it's only dependent on the direction of the coil. So let's go over that again quickly. The direction of the coil depends on which way you pick up the signal and the noise, but the signal is dependent on the magnetic field disturbances. So for the north coil, it's opposite to the south coil, but since these disturbances are eventually picked up by the way the coil is wound around the north side and the south side, the signal comes out the same way around. So when we add these two signals together, what we get is the noise goes, because this is positive, this is negative, so the noise cancels out. That's your hum. And you get double the signal, or the signals added up between the two coils. And that's basically how a humbucker works. It's pretty awesome idea. And although this humbucker is in series, what you find on Strats is that they'll be connected in parallel this way between, like, say, the neck and the middle, and it does the same thing because they're still adding it up, they're just adding them up differently. So I believe in parallel the currents of the signals add, and in series the voltage of the signals add, but it does cancel out the hum if you get your magnetic poles right. So that's basically how a humbucker works, and I hope I didn't do that confusingly. But yes, this is kind of the principle of the beginnings of how the phase stuff works, so I'll move on to that now. Okay, so let's make our way to phase cancellation theory. So here's a pickup signal. I'm using simple waveforms for this, but here's a sawtooth kind of wave, and basically anything that's represented in terms of time, or as a function of time, there's amplitude on this direction, time going past in this direction. It can also be represented as frequencies. So a sine wave would be one frequency, but a saw wave is lots of harmonics, or all of the even and odd harmonics, and they gradually decay, but it creates a saw wave. So that's a frequency spectrum representing this. That's for pickup 1. Now let's say we have another pickup 2, which has a square wave. It won't in reality, but let's go with functions that are very easy to see, or signals that are easy to see. And a square wave only has the odd harmonics. So there's the note that we hear, at the bottom, and then there's double the frequency, triple the frequency, quadruple the frequency, quintuple the frequency for a saw, and then for a square it's just the fundamental, which is the note we hear, then 3 times the frequency, 5 times the frequency, 7 times the frequency. So let's add those two together in phase, so that they're both the same way. And what we get is a strengthening of the note we hear, and then kind of the other frequencies add together. So they don't cancel. It's all nice and added. You get this nice graph, which is kind of a combination of the two graphs. So that's nice. That's 2 pickups in phase. But what we can also do is, if we change it so that the pickup is wired the other way around, or the coil is reversed, we can effectively, when we add them together in parallel or series, make it minus the signal. So here we see the signal. It's lower amplitude because a lot of it is being cancelled. But also what we see here is that in terms of frequency, the note we hear is very, very reduced. But since we're comparing saws and squares, so this is similar to a neck pickup, this is similar to a bridge pickup, very approximately, I must stress. This is just to simplify the problem. But what we see is that these from pickup 1 aren't affected, but these are taken away from pickup 2. So the note that we hear is very small, but double the frequency is an octave above, so it almost sounds like it's an octave above, because these are the frequencies series for an octave above. And that's why if you put a pickup out of phase with another pickup, you'll get this thin signal that sounds kind of tinny, kind of maybe an octave up type sound. And that's basically how the phase cancellation works when you put a pickup out of phase with another pickup, which is basically just reverse wound. Or, it's basically reverse wound. And that's how this works in the humbucker theory, is that the phase is completely opposite for the noise, but it's the same way for the signal. So when you add them together, that's why you get to cancel the noise but add the signal. And that's basically how a combination of humbucker theory and phase cancellation theory, but that's the best explanation I think I can give. But it shows that if you wire pickups the other way around, you can take away their signal from your total signal. And you'll hear that more in the demo, and it is pure tonal beautifulness. So let's move on to the other bits, like the tone pots. Okay, so let's go into tone pot theory. I would go in volume pot theory, but there's not really much point in explaining that. It's you turn down the volume, you slowly connect it more to ground, so more of the signal goes away, and it eventually turns your signal off. But tone pot theory is a little bit more different, a little bit more complex. So basically we have, here's our live line, and there's our in, there's our out, or it can be out and out, silly me, in and out. And what you'll find is basically signal is oscillating between the ground and the live, and that's sound. That's what sound turned into electricity, which gets amplified by your amplifier, and then turned into sound again when it gets to the speaker. So basically this is the tone pot. What you have is this resistor. So your tone pot is turned all the way up, and this resistor is its full value, 500 or 250 kilo ohms. And then there's a capacitor, which is connected to ground. So when you turn this all the way down, what it does is it allows for certain frequencies, due to the capacitor, to be bled away out of your signal and to ground. And this is called a low pass filter. So basically, here's this dotted line is basically the frequency that is kind of set as any frequency lower than this will pass by. And it basically cuts away the highs as you turn it down. And that's why when you turn down the tone pot, it makes the sound more mellow. So let me repeat that again. When your tone pot is full, this is at a maximum resistance, so hardly any of the signal can get to ground through there, the capacitor. But when you have it turned all the way down, the signal can split, go through the capacitor. Basically, this just takes out high frequencies and just bleeds them to ground, and then your low frequencies remain, and that's why your sound becomes mellow. Why is it oscillating? That's better. Sorry about that. Beating frequency between the phone and the light. So let's go on to the treble bleed mod, which is very similar, but this is a high pass filter. So here's your in, then there's your capacitor connected across. We'll ignore the resistor connected here, which corrects for the kind of taper of the pot. Come on, autofocus. I want people to be actually able to see this. Then here's your resistor, your volume pot here. So when you have it all the way up, this is small. It just goes across. It doesn't bother going through the capacitor. But as you turn this down, the resistance gets higher between these two lines, and then it's shorter between the ground. So the signal bleeds to ground, and some of it goes to the end. But since this resistance is quite high, it also allows, well, this is no longer the path of least resistance. So some of the signal can pass through here. And basically this capacitor dictates the frequencies that can pass high through here. So anything higher than a certain frequency can get through here. So as you turn the volume down, here's your frequency spectrum. These frequencies are turned down, but a portion of the higher frequencies can still get through because this is letting them pass via the pot unscathed. And that's why it makes it a bit brighter as you turn it up, or just keeps it quite bright as you turn it up. So that's how the treble bleed works. So let me reiterate. You have... Okay, so we kind of got cut off there, so I'll just quickly finish explaining the treble bleed theory. Basically, as you turn we'll just go over it once more. When your volume is at 10, this is bridged with zero resistance between these parts, or very little resistance between these parts, and so you get your normal tone, and it's always going to go the path of least resistance, so this capacitor doesn't really affect it that much. But as you turn it down, this line becomes more resistive and this becomes less resistive, so some of your stuff goes to ground, some of it goes to the jack, but also some of it's going to go across the capacitor because it's no longer path of least resistance. And so the capacitor lets the higher frequencies higher frequencies than it's calculated to pass, and basically what you get is a reduction in the overall volume, but the reduction in the volume of the higher frequencies is slightly less because it's being allowed to high pass through here. So a normal tone pot is low pass, treble bleed mod is kind of a high pass. So let's go on to the final bit, which is baritone choke theory. So, baritone choke theory. Here we finally are going to arrive at this equation, which is frequency equals 1 over 2 pi times the square root of the capacitance times the inductance. So, as you can see with these ones, there isn't really an inductor, but you can say technically there is due to things like the pickups, which can behave as inductors, but you can also make filters and calculate frequencies without really thinking about an inductance. But for this, it is very explicit because we have a capacitor and an inductor. So here is a frequency signal or spectrum, and you can see how we played with it with these and how we played with it with the phase cancellation theory. But basically, a baritone choke, this is specifically this kind of baritone, but basically it creates a notch which cuts out a certain band of frequencies, and the width of this notch, which is kind of called, you can call it the width, you can call it quality factor. So high quality factor is very, very thin, low quality factor is quite wide. So depending on your ratio of your capacitor and your inductor, you can make different quality factors or different widths of this notch filter in your spectrum. But so long as they're that times that equals a certain frequency, it'll always be in the same place. So you could have different values and you could be like that. You could be really, really cut out. But basically what it does is, this is your signal line, this is your ground, and in parallel you connect the capacitor and the inductor, and it just takes out a certain chunk of the signal and bleeds it off to ground. And so here is a low Q, so it doesn't attenuate the signal that much, and it's quite wide, so it attenuates quite a lot of signal, but it cuts the lows, and this is for a high value capacitor. And a mid cut, this would be a medium kind of value capacitor. And let's say it has a high Q, so this would be a very sharp drop, and it will cut out a very small band of frequencies, but very, very well. There's a medium Q, which is like kind of it dips a little bit, but it's quite wide. It's not as wide as this, but it attenuates some of the high. In this case, it's attenuating some high cut frequencies. So this is with a very high value, no, a very low value, small value of capacitor. And you can have different Q values for different things. This is just an example. That is literally just to do with the ratio of these two. But yes, if you have a set inductor, which I do in this diagram here, for low values of capacitance, you'll cut highs. And low, we're talking like 0.001 picofarad. For high values, you'll cut lows. High here is 0.047. That's not that high. You can go to 0.1 microfarad, and you'd really, really, really cut out the highs. Or maybe you'd go so low that you wouldn't even notice that much. But then you've also got like 0.01 picofarad, which is our middle cut. It just cuts out about in the middle. So that's basically how a baritone choke works. It just kind of cuts out a little band of frequencies out of your spectrum by bleeding them to ground. Similar to this, except in the tone part, it bleeds everything above a certain value to ground, or more accurately, lets any value below a certain band pass, low pass, or low pass high cut. In the treble bleed theory, it allows high frequencies to pass through, so there's a high pass. And then here it's a notch, and you can get band pass, which allows frequencies like that. But you can also classify those almost like a combination of these two. But that's basically baritone choke theory. So, I don't know about you, but that felt like a very long time. So this might end up being 2 videos, it might end up being just one long lecture for everyone who's kind of interested. But that's basically the theory of wiring, the theory of audio engineering in a guitar. Well, that was using the Joe Trohman mod. So yes, it's very late at night now. For But yes, if you decided to stick all the way through this, I hope my explanations were satisfactory to your likes, and I hope those of you who found it interesting or didn't find it interesting, just leave a comment. You're not going to hurt my feelings unless you really held abuse at me. I hope this has kind of helped you understand how the guitar was wired and why certain things were chosen because of the audio theory. And I hope you have a basic understanding of humbucker theory, phase cancellation theory, or kind of like reverse phase theory. Have a basic understanding of tone parts, treble bleeds, and baritones, and there's many other ways of wiring guitars, but this is just one version. I could go through so many different things. The Crow has different things. Sure, a little bit of how the Holly Benton Les Paul is wired up. I did a little segment a while ago about tuned versus traditional coil taps with the LPJ, but I hope you've had fun. Hope you've learned something, and I hope you look forward to the video where we actually play the thing. And if you picked up some of this, you'll probably appreciate and understand how the sounds are created in the next video. So take care, and as always, ciao for now, and thanks for watching.